Alright, this is thermal continued, so alright, so far we just talked a little bit about heat, okay, or lowercase q, right, in our equation. That's the variable in our equation. And the equation for heat is this. Alright, now this is the equation we use when heat is causing a change in temperature, alright, of a substance. This is when heat is causing a change in temperature of a certain mass of a substance. That's when we would use that. Now there are times when heat is released or absorbed in other circumstances. For example, a change of state. Okay, if something is changing state from a solid to a liquid or from a liquid to a gas, there's a heat exchange but not a change in temperature. And we're going to save that till later in this unit. Another case is heat exchanges in chemical reactions, and that's really where we want to focus in this unit. Heat exchanges in chemical reactions. Now, basically, I think I mentioned this at the beginning, that what we're talking about is energy transformations. So in chemical reactions, we're talking about transformations between chemical potential energy to heat, or vice versa. So heat energy or thermal energy into chemical potential energy and vice versa. Let me just give you an example of this. Hang on here. Here's an example. If I take carbon, solid carbon, and I react it with O2 gas so that I get CO2 gas, what will happen is this will also produce heat, 393.5 thousand kilojoules. Now, there's a few observations we can make about this. One is that that's a pretty high number. So far, we've been working with numbers in the joules, right? Like on this lab, when we look at specific heats of metals, we're talking about point something joules per gram per degree C, right? Low numbers. When we're talking about chemical reactions, we're usually talking kilojoules. So these are 1,000 joules. Now, what does this mean? If I write this like this, by the way, this is called a thermochemical equation. If I write this like this, what I'm saying is that 1 mole of solid carbon, the little s means solid. In this unit, the phase symbols become very important because there's a big difference between producing a solid and producing a liquid in terms of heat. Okay? And if I'm adding 1 mole of O2 gas, the G is for gas, then we say produces 1 mole CO2 gas plus 393.5 kilojoules of heat. Now, of course, this is a combustion reaction. This is the combustion of carbon. So charcoal is burning. This is charcoal burning. Charcoal's burning, and as the charcoal burns, of course, it gives off heat. Heat is a product. Okay? So heat is a product here. Of this reaction. when heat is a product, the reaction is called exothermic. Maybe you've heard that word before. Think exterior, outside. The heat's coming out. Exothermic, out. The heat is moving out of this reaction. Right? It's giving off heat. If I was holding a container that had carbon burning in it, the container would feel hot or cold? Hot, right? Because the reaction's giving off heat. Right? So the reaction's giving off heat into my hands, or if I'm sitting around a campfire, the campfire's giving off heat, right? Now, if I turn this reaction backwards, let's say I wanted to take CO2 gas and I wanted to break it down into carbon and oxygen once again. It would require the same amount of energy. Now, I might not have to put this energy in as heat. I might be able to put it in as electrical energy, for example. But that's what it would require. So notice the reverse reaction. The reverse reaction requires the same amount of heat that the forward reaction produced. Absorbs. Absorbs requires the same amount of heat, or energy, I should say. Energy is typically given off as heat, but it could be given off as light, but it'd be the same amount of energy. So if this was giving off light as well, you'd have to count that into the total energy being produced, or subtracted from, whichever way. It'd have to be added in there. The reverse reaction requires or absorbs the same amount of energy as the forward produces. By the way, this is always true. Okay, this is one of the rules of thermodynamics. So we'll call this Rule 1 of thermochemistry. All right, if you reverse the reaction, it's the same amount of heat. It just goes in the other way. All right. Now, this type of reaction is called endothermic. So when a reaction requires heat, or requires energy, it's called endothermic. Let's get some more examples here. All right, let me give you another example. This is one that you saw in the laboratory, 2H2 gas plus O2 gas yields 2H2O liquid plus, let's see, 571.6 kilojoules. Now, did you give off that much heat with your little rockets? Is that how much heat you got? 571,600 joules? Enough heat to raise the temperature of 1 gram of water? 571, well no, it's divided by 4, so 100,000 degrees? I don't think so. Right? Why? Why did you get so much less heat? Yes? Exactly, you didn't use a mole of gas. A mole of a gas occupies 22.4 liters at 0 degrees C. So if you had a 22.4 liter bottle of oxygen and a 22.4 liter, and actually no, you'd want 44.8 liters of hydrogen and 22.4 liters of oxygen. Put those all together and light a match at the end. Now you're talking. Yeah. What's that?
We should try that.
I don't think so. Now, if we wanted to switch this around, again, just to emphasize the point here, I'd have to put in the same amount of heat. Whoops, sorry. See? So it was exothermic. Now, by the way, this process right here actually has a special name. This is called electrolysis of water. And let me pause this actually and show you an example of this. Or maybe I'll get this set up. I'll get this set up at the break, but don't let me forget that. I want to show you a demonstration of this here. Now, there's another way of writing thermochemical equations. Another way of writing thermochemical equations, and that is, instead of actually putting the heat right into the equation, I take it out and I write it as something called delta H. Okay, now, one thing, what you see here in looking at this, you'll see the same number. All right? Actually, I messed up here. This should be a negative sign. So you see the same number, but what's different is, for one thing, you see a negative sign. And the other thing, of course, is you see this weird thing here, delta H. So what is delta H? Well, we know that delta just means change. So what is H? That's the question. H is a new property called enthalpy. Well, it's a new property for you, probably. It's called enthalpy. Why they chose H for enthalpy? Well, I know why they didn't choose E, because they were using E already for energy. So they didn't want to, this is a specific type of energy. Maybe for heat. Because see, here's the thing, enthalpy, H, or delta H I should say, is equal to Q for processes happening at atmospheric pressure. So basically, if you're in an open container, if it's a process occurring in an open container, this holds. In other words, this is not true in a gasoline engine. This is not true. Delta H for the gasoline burning in the engine is not equal to Q for the gasoline burning. And that's the reason, because the reason is most of the energy is actually being given off as work, or it's being produced as work that the engine is doing. But this is what you need to know, because all the stuff we're going to be doing this class is going to be at a constant atmospheric pressure, in other words, in open containers. I should say constant. Yeah, no, actually, let's leave that. Open containers. So delta H is equal to Q for processes happening at constant pressure. And the way that we maintain constant pressure is by just using an open container. And we are, I guess, in terms of thinking about H, because I mean, you can look at H in a couple ways. One way is just this: just say delta H is just equal to Q for the process. All right, under the circumstances, in the circumstances under which we're going to be working. The other way to look at it is this: that H is chemical potential energy. H is chemical potential energy. Now this should make sense at this point, because if you remember just a little while ago up here, I said that in chemical reactions, what we're talking about is transformations between chemical potential energy and heat. When a chemical reaction happens, what we have is a transformation of chemical potential energy to heat, or vice versa. Okay? Now if you look down here, you see H is chemical potential energy. So it makes sense, therefore, that delta H is equal to Q. Do you follow me? If there's a change in chemical potential energy, that difference is given off as heat. Let me show you this in a diagram. Now you've seen some diagrams kind of like this before, potential energy diagrams that we did when we were talking about bonding. We're going to make them look a little bit different now because we're drawing them for chemical reactions. If I put enthalpy on this side, now if you like, when I say enthalpy, think chemical potential energy. This is the potential energy of the molecules of the atoms or whatever's involved here. Here's how I would draw the reaction that we just looked at. 2H2 plus O2. And then what I would say is that the two water molecules are actually at a lower potential energy state than the H2 and the O2. So when this reaction occurs, there is a negative change in enthalpy. Delta H is less than 0 because it's going down. You see that? Now, here's what this means. Somehow, H2 and O2, the pure elemental gases, somehow they have more chemical potential energy than the H2O. The system has greater potential energy. All right? So that it will go. Now remember, systems always move. We talked about this when we're talking about covalent bonding. Any kind of physical system always moves to where it has the lowest potential energy. I use the magnets to illustrate this. If the magnets are farther apart, do they have greater or lesser potential energy than when they're close together? Greater or lesser? When they're farther apart, they have greater. potential energy. Why? These aren't going anywhere. They're already there. They're already at their lowest potential. These, they want to move. Okay? So if you look at this diagram, what we're saying is those hydrogens and oxygens at the top of the hill, they want to move. They want to go down to the bottom. They want to go to where they're actually more tightly held. Okay? What's really happening here, the picture in this diagram is showing you, is that hydrogen and oxygen have a greater attraction for each other than they do for themselves. Hydrogen and oxygen have a very strong attraction for each other, not so much for themselves. If you've ever gotten ditched by your best friends for someone of the opposite sex, you totally understand what's going on here. Hydrogen's like, hey, hydrogens, you're cool and everything, but I'd rather hang out with oxygen. That's basically what's happening here, okay? Now, of course, it's really about bond strength. In fact, we're not going to get into it in here. But if you look at the actual energies of the bonds themselves, you can calculate delta H for the reaction. Because what's going on here is the H2O bonds are stronger than the bonds here and here. They're basically stronger. So what's happening is it's like I have two weak magnets hooked to each other here. And then I can make a stronger bonds by separating these things from each other and hooking them up to the other ones. These would be stronger bonds. The analogy doesn't work great in this case, but that's the idea. Let me say it one more way before the break. Remember, when we talked about bonding, I think I mentioned this. Bond formation. Did I say this? Bond formation always releases energy. Maybe I didn't say this. And bond breaking always requires energy. So what we're saying in this case, now these are true. And so what we're saying then in the case of the formation of water is the formation of the H2O bonds of 4, and there's going to be 4 of them, 4 hydrogen to oxygen bonds in water, releases more energy. Than is required to break these. So there's lots of different ways to kind of look at this. This is one of them. We can say that because the formation of the hydrogen to oxygen bonds in the water, that releases more energy than is required to break the H2 and the O2 bonds. That's why this releases heat. Because see, this heat right here, conservation of energy. If you're going to go down in potential energy, you must be giving off energy. The difference is released as heat. So let me add that to this statement. The difference is released as heat. All right, let me stop there because I want to get a little demo ready for you after break. And we'll take questions there too. Okay, unfortunately, you people watching at home missed the whole demo here. but we're going to, let's make an energy diagram of what we just saw. So just to draw it, we've got our fork here. So if you're watching at home, you could do this yourself. Put a piece of onion bag around a couple of forks. Okay. Put some baking soda in the water. Then hook these forks up to a battery. All right, and you make oxygen and hydrogen gas at either side. So this will drive this reaction. And we have to have an input of, what was it, 571? 571.6. kilojoules per mole. Now, we didn't make a mole. Remember, I said a mole of a gas is 22.4 liters. I didn't make anywhere close to that. So I didn't use 571.6 kilojoules. By the way, that's the next step. We can actually use stoichiometry to figure out how much energy is required to make a certain amount of this stuff. So we could calculate, if I knew the volume of hydrogen and oxygen that I just made, I could figure out exactly how much energy I just used to do that. Using this proportion, 571.6 for every 1 mole of oxygen and 2 moles of hydrogen. Now, if I draw my little energy diagram, what I was doing is this. I was starting with 2 moles of water, which were down here in my enthalpy scale, in terms of potential energy, and I was boosting it up in potential energy. Now, this might seem kind of weird, but think about it like this. It's like pushing a ball up a hill. I was using the battery to push the chemical ball up the chemical hill. And as soon as I allow them to go backwards, they will roll back down. And I could do this for all eternity, like Sisyphus. I could just keep rolling this up the chemical hill and letting it come back down, and rolling it up and shaking my fist at the gods. Now, this required energy, right? So see, I can draw it like this on my diagram now. Energy goes in. Now, I'm hoping this kind of diagram is ringing another bell in your mind, and that is electron energy levels. Think about this. Electron energy levels. Photon comes in, hits the electron pops up an energy level, right? And the electron goes down, what happens? Photon comes out. Same thing here, except it's not photons. There are actually, it's pretty cool, there are chemical reactions that you can drive with light. Particularly like UV energy. You put UV energy in them, you can make them happen. There's a lot of decomposition reactions that are driven by light. Sunlight, there's some things you don't want to leave out in the sunlight because it will degrade them, right? It'll cause them to decompose or discolor or whatever. So light can drive chemical reactions. All right, the moment you've all been waiting for. Stoich with heat. Stoich with heat. So, first of all, let's take our little chemical reaction here. We're going to say, let's say I made, let's say I made 0.010 moles of O2 gas. 1/100. I don't even think I made that much, but let's say I made that much O2 gas. How much energy was required to do so? Well, I'm going to look at my equation, which said 571.6 kilojoules, right? Plus 2 moles of water, liquid water, produces 2 moles H2 gas and 1 mole O2 gas. So here's what I'm going to do. I'm going to use this to make a conversion factor from O2 to kilojoules. What this tells me is that there's 571.6 kilojoules per 1 mole of O2 gas. If I wanted to use hydrogen gas, it would be per 2 moles of hydrogen gas, right? So if I start off with my moles of oxygen gas in my conversion here, I just multiply by this, pretty simple. And I get, what, 5.716 kilojoules. That's still a fair amount. That's 5,700 joules. And that's only make a little bitty amount of oxygen gas, right? I remember an old MacGyver episode where, who said, "Oh God"? No, it wasn't you. Hey, MacGyver was my inspiration when I was young. So he was locked in this room, and the guy, the KGB or whatever, they were like pumping the air out of the room. Now, he always does this. He's got this kind of, he looks around and he's got ordinary stuff in the room. So there's like a 55-gallon drum of water in the room, and there's like a stack of car batteries in the room, and jumper cables. I don't know where he was, but that's what he had in the room. So he rigs himself up a giant electrolysis apparatus and just starts cranking oxygen out of this 55-gallon drum, which gives him enough time to figure out how to break out of the room before he runs out of oxygen. Yeah, you do have to be a little careful. One of the things that could happen here, obviously, if you're in a sealed space, you're generating hydrogen, oxygen, gas, and sparks. That could be a problem, right? Because all that hydrogen and oxygen, you know, MacGyver was not necessarily realistic. I hate to break this to you guys who are big MacGyver fans out there. It wasn't always realistic, the things that he did, okay? All right, so this is the simple way to do it. Now, I want to show you, though, because on the worksheet I'm about to give you a worksheet. You'll see, you might see this written a different way. Oh, don't even mention Bill Nye the Science Guy in my presence, please. Okay.
We should watch him. He's my hero.
I hope he's watching this YouTube video right now. All right. Hey, folks, look at this. Delta H is positive in this case. Think about it like this, folks. Look, there's two different ways of writing these. Notice the two ways I just wrote this right here. These are absolutely equivalent. So look at this one right here. See how I have the heat coming in on the left-hand side as a reactant? And then look what I did over here. I took the heat out of the equation. I wrote delta H, and then I wrote it as a positive. Just remember that delta H is equal to Q. Q is positive when something is absorbing energy. It's absorbing heat. So in this case, when the heat is on the left-hand side, when it's a reactant, that's an endothermic process, and delta H is going to be positive. If I flip it around and heat is a product, then delta H is going to be listed as negative. Because it's always from the perspective of the system. In this case, what's the system? The system is the reaction that's happening. Is the reaction losing or gaining heat? In this case, gaining. Is reaction, another way to say it is heat going into the reaction or coming out of the reaction? Let me just write the reverse here again, just in case you're still confused about this. H2O, H2 plus O2 yields 2 H2O plus 571.6 kilojoules. If I wanted to write this a different way, I would write it like this. Delta H equals negative 571.6 kilojoules. See the difference there? The heat is leaving. It's going out. If you're spending money, what's the change in your account? The change in your account balance is negative. You're spending money, right? If you're making money, the change in your account is positive. That's endothermic process, right? Spending money is exothermic. By the way, it's much easier to spend money, isn't it? Than to make money. Yeah. Kind of like chemical reactions. I mean, remember, exothermic reactions are more popular out in nature. They're easier to happen. They happen more easily. Okay, let's try some of these. Let me give you a little worksheet. So in number 1, got 2 S.
Well, you make
What's sulfur? 32.07? All right, so I got the first one up there for you. Hey, folks, in a case like this, if it's asking, if the question is worded such like this, it says, how much energy is released, then I would accept it if you just said 159 kilojoules, because that's what's released. However, if you write negative, I'll know what you're talking about, because this means negative is telling me it's being released. All right. Why did I put it in as negative? Because it was negative up here. It's delta H. Yes? Yep, I did right here. Oh, did I do that in my calculator? Oh, did I miss that? Oh, sorry. Okay. Very good. Negative 79.5. Okay.
Yeah, you're still.